get started with integration. So integration, or taking an antiderivative, is the opposite to doing a derivative. So if I have some derivative function here, right, so you can see that it's like d f of x with respect to dx, right? That's taking the derivative of the function f of x with respect to dx. If I want to reverse that and find the original function f of x, I can do this operation known as an integral, right? And a lot of you would have already been, would have encountered this maybe in unit 1 and 2, and probably as, as like from school as well, hopefully. If not, that's all good. It's always good to get a head start on your school. So the integral will always spit out the original function that was like derived, I guess, initially. So it'll spit out f of x. And another thing you always need to write with an integral is this plus c. So a lot of you know that when you take a derivative, right? So if I take the derivative of a constant value, maybe something like 4, right? 4 is constant. It doesn't change with any variable. That's going to be equal to 0, right? And so if I have a function like x squared plus 2, if I take the derivative of this function, right, I'll get 2x. That plus 2 is just gone. So if I'm integrating 2x with respect to dx, sure, I'll get the x squared part, right? But I won't get the 2, because in my mind, that 2 just doesn't exist, right, when I'm doing the integral. So to sort of cover for that, we write a plus c. And our plus c is any real number, more or less, right? And sometimes they'll give you enough information to solve for what c is, right? So maybe they'll tell you that it goes through the point 0, 2, and using that you can work out what plus c is, right? But yeah, make sure you include that. Usually you'll lose marks if you don't. There is one case where you won't, and sometimes they'll ask for like, oh, that's too many n's. They'll ask for like an antiderivative or an integral of something, and that just is one solution, right? So adding the plus c gives you, like, shows you that it's a family of functions. There's multiple solutions. If you don't include the plus c, you're only saying that's the one solution there is to that integral, right? Another thing to not forget is the dx. So what that says is that when you take this integral, you're doing it with respect to x, right? The change that you're trying to reverse is that change that's been done to x, right? Maybe you'll be sometimes, if you guys are doing like sort of those physics application questions, you'll be dealing with functions that are with respect to time. So when you integrate that, you need to change that to dt, right? So make sure that d whatever at the end is consistent with the actual variable you're integrating, right? Otherwise, you will lose marks. In some questions, you'll see that the antiderivative is represented by a capital F of x, and that just generally like refers to the original function, or the function that's being anti-derived. Usually, the question will just tell you because they don't want to confuse you with random stuff like that. Cool. Let's go through some integration rules, and then maybe we'll have a crack at doing a practice question. Okay, so some rules with integration is that if I'm taking an integral and I'm multiplying it by some constant, which is represented by k in this case, that constant can just be dragged out to the front. So what do I mean by that? If I've got the integral of 5 of f of x doesn't really matter what it is. It could be x squared, right? That's the same as taking the integral of 5 times the integral of f of x with respect to dx, with respect to x, sorry. So it's a relatively straightforward rule, but it can save you a little bit of a headache when you're trying to integrate something, or you're trying to change an integral to make it fit a rule. So that is quite useful to know. So yeah, make sure this is a rule that you guys are really familiar with. It should be in your like formula sheet that they give you, but I think this is a relatively simple rule to remember, so I hope you guys all remember this one here. Another one that I think is a little bit more tricky to understand, but is probably more important than the last, in the sense that it's quite particular to some question types, but it is sort of those high yield topics where often they'll ask you like a lot of questions from that same bit. So splitting up terminals. So we'll talk a little bit more about definite integrals in a little bit, but basically the fundamental theorem of calculus, right, is that if we have a definite integral, right, like so, what that means is that we find the original function, represented by capital F, and then we sub in the values of the terminal, and then we subtract them, like so, right? What splitting up the terminal says is that, let's say I have some function, right, that looks a bit like this, right? If I want to take the integral from a to b, right, and I, have some third point I know as well, maybe some point C, right? I can take the integral from a to c, which is represented by this, and then add that to the integral of c to b, which was represented by this. And you can see from the shaded area that I've shaded in, that still represents the total span of that integral, the total area represented there. We'll talk a little bit more about area under the curve as well when we talk a little bit more about definite integrals. So if you're a little bit lost on this part, don't worry too much. Just know that you can split up definite integral terminals like so. So I'll sort of touch on this again when we do a definite integral question. Okay. Another thing we can do is that if we have two functions that are being added, it's really important that they're being added. If they're being multiplied, you can't do this. If they're being added, you can just split them up into two different integrals like so. So sometimes it can make, if you see a function like this and you get pretty confused and you don't know how to integrate it all in one go, that's all good. Or maybe you're just double checking your answer. It's perfectly fine to just split it up into two integrals like this. Right? What's not fine is having an integral like this, right? And splitting that up into something like this, right? Like this doesn't work. Sorry, my integrals are a little bit wonky today, but hopefully you guys, this wasn't a horrible integral, but whatever. Oh, I just realized the camera cuts that off. That's my bad. I'll rewrite it again. So what you can't do is this, right? So if you have the integral of x cubed dx, you can't split that up into this. And so just keep that in mind when you're sort of doing this rule. I see a lot of students get confused with this. Also, when you do split it up, one thing to note is that these terminals remain the same, right? You're still integrating over, that terminal, but you can also do it with indefinite integrals. What I mean by indefinite integrals are integrals without those terminals, or end and starting and end points. Okay, another cool rule is that we can reverse a terminal, right? So if I'm taking an integral from a to b, so the starting value is a and then we're ending up at b, that's the same as taking an integral from b to a, but with a negative out the front. How can I show this? It's all to do with the fundamental theorem of calculus again. So a to b of f of x, right, like I said earlier, is equal to capital F of b minus capital F of a, right? Now, if I do the same for b to a of f of x, like so, that's just equal to f of a minus f of b. Now, I'm sure a lot of you can already see this, but if I try to factorize this expression just by taking the negative out, I'll get negative f of b minus f of a, like so, with a negative out the front. And you can see that these two are just, you can see that these two things here are just negatives of each other, right? So this rule sort of stands. Hopefully that makes sense. It is super useful for solving these multiple choice questions that I'll show you in a little bit. Some basic rules with an integral. These are just to follow. Well, these are rules that you have to follow. They are in your formula sheet as well, but I would recommend memorizing them. Just because you don't want to be in exam one flipping through that formula sheet and trying to fit these rules to these weird integrals that they will give you. So it's better to just know them and understand how they work. And the best way to understand how they work is to just do a bunch of practice questions. Okay. All right. And this is just them in sort of a different form. So I definitely recommend putting this in your bound reference and also this one in your bound reference. But more than that, I would recommend just understanding it entirely, right? Okay. So I sort of mentioned this. We can take an integral or an antiderivative between two bounds, right? And that just happens to give the area under the curve. Now, I won't go into the reason as to why that gives the area under the curve, but if you are interested, there are really good explanations online that sort of go into this. The only reason I won't go into it is that it's out of the scope of methods, and it's not really something you need to know, but if it is out of interest, a quick Google search generally gives you a good answer for that. Okay, so I've sort of already mentioned the fundamental theorem of calculus, just shown here. I've written out plenty of times earlier. So hopefully that makes a little bit of sense. So again, capital F of x is just the antiderivative of lowercase f of x. Now, in this case, you guys would have noticed that plus c is gone. The dx still remains because we're just saying what we're actually integrating. And in this case, we're integrating a function with x, right? But we can get rid of the plus c. And the reason that is the plus c sort of cancels out. So if you guys go ahead and try to do this, you will see that the plus c cancels out. So we'll see that with the first f of b, right, we'll get f of b plus c, right? That's the first sort of set. And then the next one, we'll get f of a plus c like this. And you can see here that the plus c's just cancel out. So there's no point including them in the first place. So for that reason, we sort of just don't include plus c at all. All right, let's go through an example question. You know, if you guys, when you guys are watching the recording, feel free to pause maybe and type your answer in chat as well after you get a solution for it, or feel free to follow along. So yeah, either or is fine. I would definitely recommend having a crack at it first before just looking at my answer or looking at the way I'm doing it. Okay, so the question is, it's to evaluate a definite integral. So from 0 to pi on 2 of sine 4x plus 4x cubed with respect to dx. So what we're going to be using is that table that I showed you guys a few slides earlier, and also the fundamental theorem of calculus to sort of evaluate this expression. So the first step is to integrate it, right? So to integrate this, I just used those like the integral table that I showed a little bit before. So if we integrate sine 4 of x, we get negative 1 on 4 cosine 4x. And if we integrate this, we just follow the integrating a polynomial rule. And so we add 1 to here and then divide by that, right? So we add 1 to the top. So 3 plus 1 is 4. Divide by 4, and we get this, right? Relatively simple, hopefully. And then after this, now we apply the fundamental theorem of calculus, right? So what I've done here is I've subbed in pi on 2 into the calculated expression from earlier. Then I've subtracted that from subbing in 0. So really all I've done is f of b minus f of a, just following fundamental theorem of calculus, right? And then from there, it's a matter of evaluating it. Now, evaluating it can be a little bit challenging, especially with these sorts of long questions, right? Personally, when I did these in high school, I made a lot of mistakes in these sorts of questions. So what I would do is I'd actually write it out like this, right? I'd take it step by step. I'd break it down into smaller manageable bits, and then from there I'd start doing the hard maths, right? Like this 4 pi on 2, before even calculating what it was, many of you can probably just look at it and know what the answer is. I just solve like what 4 pi on 2 is, right? So I would just write it out like this, right? Which is like a reasonably trivial calculation to do, but you'd be surprised at the sort of mistakes you guys would make under exam pressure. At least I was. I made a lot of silly mistakes, and so a lot of what my exam preparation was and my SAC preparation was just trying to cut down on those silly mistakes. Anyways, I'll probably talk about that a lot as we go through the session. I'll talk a lot about the methods I use to eliminate my silly mistakes, and maybe how you guys can apply that to your working out. So one method I always used was writing out my working out in every single step, right? Just because it helps with it. When you go back and read through your working out, you can sort of see all the calculations you've done, and then from there, see if you've made any silly mistakes and sort of make sure that you've done it correctly. Okay, so from there, you're just sort of evaluating all of this. So this is an exact value you guys need to know, and that's going to be 1 here. And that's also equal to what cosine 0 is, and that's also 1. And so from there, you can sort of just work this out. So hopefully that makes a bit of sense. And this is what our final answer would be. This also gives the area under the curve for this function from 0 to pi on 2. And when we evaluate that, we get pi to the power 4 by 16. So hopefully you guys got a similar answer. Okay. So this is just a multiple choice question from a VICA exam. So you guys can see 2019 exam 2. If you guys are interested in the statistics, like what percentage of students answered A, B, C, or D, you can check that, or E. You can check that out on the VCAA website. They do obviously they show the correct answer. They don't show the working out too much, which is kind of annoying. But what they do is they do show you like the distribution of students of like where they who selected each option, which I think is pretty interesting. But yeah, if you guys are interested in that, check that out. Anyways, so how can we do this? So let's see what the question is asking us, right? So we're asked to find the integral of f of x, and we don't know what f of x is. They haven't told us what f of x is, and a lot of people would see this, freak out, and just skip it, right? But we're going to try to break it down and see how we can go about tackling these sorts of questions. So we've got f of x with respect to dx is equal to 4 from 1 to 4, right? We're taking the integral bounded from 1 to 4, okay? And they've also told us that from 2 to 4, it's equal to negative 2. And what they want us is to evaluate this. Okay, so how do we do it? Well, I want to try use these two integrals that they've given me and try fit that into this integral and try work it out. Okay, so what does this first integral tell me? It tells me that capital F of 4 minus f of 1 is equal to 4, right? The second integral tells me f of 4 minus f of 2 is equal to negative 2, right? And then if I work out what this integral is here, right, I get capital of f of x plus x squared over 2 integrated from 1 to 2. So now I just sub that in and I will get this expression here. Then it's a matter of simplifying that expression. So I see I get f of 2 minus f of 1 plus 3 on 2, right? That's still not enough information for me to eliminate any of the options, which kind of sucks, but I guess we just have to sort of deal with it and work through it. Ideally, as you're working through a multiple choice question, you're able to eliminate options as you go, but with these sorts of questions, it's a little bit hard to do that. Okay, so maybe some of you guys can see where this is going, but we're going to be using simultaneous equations to work out what f of 2 minus f of 1 is equal to. So I need to manipulate these two equations to make the expression f of 2 minus f of 1, so I can sub that in. So what I do is I subtract the red equation from the blue equation, and conveniently when I do that, I work out that f of 2 minus f of 1 is equal to 6. And so then I substitute this into here, and I get 15 on 2. So my final answer is option E, 15 on 2. So hopefully you guys got a similar answer as well. Any questions with how, like the method I use to work this out, just drop them in chat and I'm happy to answer them as we go. Okay, another useful property of these definite integrals, right, is that we can use it to find the area bounded between two curves. A lot of you will be used to just finding an area bounded between, like a single curve. So you've got some curve like this, and maybe you're just finding it between the x-axis and the function, right? But what we can also do is if we have two functions like that, we can actually just, oh, that's a wonky line. I'm gonna get rid of that graph. So if I have two functions like this, I can use definite integrals to find the area contained between those two functions, right? Which is quite nifty. There can be some practical applications to this, but in methods you don't really cover that. Sometimes they give you application questions where that's useful. Maybe you're trying to find the area of a garden bed or something similar to that, and that garden bed is defined by multiple functions. That's just an example of the sort of application question you could get here. So the way, like the general equation that we always use for this is that contained area is, well, first you need to solve for the x-intercepts, right? So lower x value refers to the lowest x-intercept between those two functions. For example, if I have a function like this, right, and I want to find the area contained, well, I need to work out what this x-intercept is and what that x-intercept is as well, right? And then from there, I can sort of work out that area in the middle. Okay, so you want to work out what those lower and x values are, and then you want to determine in that region which function is the upper function and which one is the lower function. So in this case, I'm going to call this line g of x, I'm going to call this line f of x. So we can see that in this region, right, from, let's say a to b, in the region from a to b, g of x is above f of x, right? And so g of x, in this case, would be upper curve, and we'd be subtracting f of x from that. Now, let's say I wanted to take the integral of a function that's like this from maybe here to here, right? So call this b again and a again, right? So in the first period from that first intersection, right, in just this area here, the top function, let's say, is g of x, the bottom function is f of x. Right. Now, when we go here into this period, right, so let's just call that middle point C, from C to B, that top and bottom switches, right? So now we have f of x at the top, and we have g of x at the bottom. And when we do this, what we need to do is we need to split this up into separate integrals. I need to take an integral from A to C, and then from C to B to like separate integrals because we're changing the upper and lower. Hopefully that makes a bit of sense. Okay. So here's an example question. Have a crack at it, and we'll sort of go through the answer. Also, feel free to work with me along as I go through it. Okay, so what it wants is the area bounded by the lines of y is equal to x squared, y is equal to 0, and x is equal to 3. That's sort of represented on this diagram here, the one that I've sort of scribbled on, sorry about that. But we want this area here, right? So they said y is equal to 0, y is equal to x squared, y is equal to 0, right? And x is equal to 3, right? Okay. How can I do that? Well, I want to determine what the lower and upper x values are, right? So, well, the upper x value, right? So this is just the representation of the area, sort of. The upper x value is clearly going to be at 3, right? Because that's where that intersection point is going to happen, because that's where that line is, right? So this is at 3. It doesn't really matter what y value it is at, because we're not actually using that for the integral. The starting value at y is equal to 0, right, is at x is equal to 0, right, which is quite convenient. Okay, now the upper function in this case is x squared, right? But what's the lower curve, right? We never defined a lower curve. Well, the lower curve in this case, right, is going to be the x-axis, right? And the x-axis is given by the equation x is equal to 0. So that's why I subtract with 0. Okay. And so from there, it's just a matter of evaluating this integral and, you know, using the fundamental theorem of calculus, summing values in, and then, you know, giving your answer. Now, this unit squared stuff is not entirely necessary. I usually write it. Sometimes I'll write it like this, right? And now it's just out of habit. That's not something you need to write, and it's perfectly fine to not write it, because oftentimes you'll see in Vika's answers that they don't have that unit squared stuff. Sorry, they don't have that unit squared stuff, so nothing to worry about too much. But yeah, so you can include, basically my point is you can include it or you don't need to include it, doesn't matter too much. Okay, integration by recognition. So integration by recognition is a really common question type, and it's not a particular topic per se, but it's a really common question type. I've definitely seen it in a bunch of exam ones in particular. Why exam ones? The whole idea with integration by recognition is that you're given an integral that you won't usually be able to solve. Usually they're in the form of like some two functions multiplied by each other, like this, right? And a lot of people will be like, well, can't I just split that up into two integrals? No, you can't. They're not being added, right? They're being multiplied together. Okay, so the way we do this is this technique known as integration by it's by parts, or IBP. That's out of the scope of the method study design, but there is also another way to do it. So the way methods wants you to do these questions is, well, first they'll give you a function to integrate, right? Or differentiate. They'll give you a function to diff, and then from there you need to work back and find a different integral. For example, we have this part here, and it's usually part A. So they'll be like differentiate some function, right? And then they'll say hence find the integral of this, right? So the first step is to just differentiate, right? Do it in the order they want, right? So we're first going to differentiate x log base e of x. I think it's just the formatting, but this should have just been, you know, natural log or log base e. Okay, hopefully that's not confusing anyone. Okay, so we're going to take the derivative of x log e of x. I'm going to give everyone a couple seconds maybe to just type in chat quickly what rule they think is being used here. If you guys said product rule, you would be correct. So since these are two functions being multiplied by each other and we're taking the derivative of them, we want to use product rule, right? So a quick recap of product rule. So if I have dy dx, right, where y is equal to two functions, u times v, the first thing we do is we do u times dv dx plus v times du dx. Cool, so that's all I've done in this part. All right, so once I take the derivative, I get 1 plus log base e of x. Okay, cool. And then we want to integrate it, right? So if I integrate log base 1 plus log base e of x, I get x log e of x plus c, right? And so then I can do a little bit of rearranging to work out what the log base e of x is actually after doing this, if that makes sense. So ideally we want to get, we got 1, I'm going to write it as ln. That also just means natural log. So we have our derivative as dd of x ln of x, right, is equal to this. Okay, and I want to integrate ln of x with respect to dx. Okay, so what do? I rearrange this equation for ln of x. So ln of x is equal to d dx x ln of x minus 1. And then I substitute that into there. And so then this integral is equal to dd of x times x ln of x minus 1 dx. Okay, and so when I take the integral of a function that's being like derived, I guess like that, the integral and the derivative just cancel out. So what I'm left with is x ln of x plus c, right, minus the integral of, you can't really see that, but basically it's just this line here. So x, x ln of x plus c minus the integral of 1 dx. The integral of 1 dx is just x, okay? So that's just x ln of x minus x plus c. Sorry, my writing covers that, but the answer is still the same. Cool, hopefully that makes sense. And hopefully my scribblings aren't getting in the way. The scribblings won't be there on the notes, but the notes will have the full solutions.